So next up is this theorem that states how we find a distribution function or a PDF for a new random variable for the case of continuous random variable. Okay, so let's read the statement of the theorem and then complete it. Okay, let's say f of x is the probability density function of continuous random variable x. Okay, so we know information about x through this PDF. Let's define new random variable y through this new function. And let's assume that this function g is monotone in the support of x. Doesn't have to be monotone outside of support, so it's really crucial to check the monotonicity within the support of x. Then, if this assumption is satisfied, then the PDF, there's a tiny typo, just the one dot. The PDF of new random variable y is given as follows. Okay, so I'm going to denote the PDF of y as f sub y. So maybe it's better to put f sub, the subscript capital X for the PDF of x. Okay, so the PDF of y is given as follows. What we do is we are going to obtain the PDF of y through the PDF of x by plugging in inverse of g. That's why g has to be at least monotonic or 1-to-1 within the support of x, and multiplied by derivative of the inverse function. Okay. Okay, so let me write down what each component is in words. So what the expression on the right hand side is about is you solve y equals g of x for x and then plug in x, okay, in terms of y. Okay, you are replacing x in the PDF of x by the inverse of g of x, which can be expressed in terms of y. So on the right hand side, we left with the expression only in terms of y, right? And the thing that within absolute value is derivative of inverse of y, inverse of g with respect to new random variable y. Okay, so which is called Jacobian. Okay, right. So let me give you a little bit of explanation where this theorem comes from. It's not a technical proof for this theorem, but it is enough to give you intuition on why the theorem, how the theorem is stated. Okay, so let's think about the case where y is just as simple as 2x. Okay, so this is monotone. Okay, I'm not gonna give you explicit this information about random variable x because we don't really need it. Anyways, no matter what support of x is, this new function g of x, which is 2x, is monotone in all entire real line. Okay, so for example, if you think about probability of x being within, say, 0 and 3, okay, then this probability is obtained through the integral from 0 to 3. Again, we are dealing with a continuous random variable. Integral from lower bound, upper bound of the density function of x, right? That's how we would obtain it. But if you replace x by, if you solve this g of x for x, then what we have is x equals to 1 over 2y, right? So that is the same as y being, half of y, which is indeed x, being between 0 and 3, which is the same as probability of y in between 0 and 6. So in this case, if we would know the density function of y, we would have to compute this following integral, right? Where f sub y is density function of y. So we would integrate density function of y from 0 to 6, right? Right. So I'm going to go back to this, and instead of thinking of this probability, I'm going to directly transform this integral through this expression just using the transformation technique we would use in calculus, okay? So here, this integral can be obtained as follows. Let me say this, it can be transformed. Can be transformed. So this integral, if you replace x by y, then whenever x is 0, y is 0. Whenever x is 3, y is 6. And the same function, f sub x, and instead of x, it is half of y, right? And dx is half of 2y, right? So that is going to be half of 2y. So dx is replaced by half dy. That's how we do in calculus, right? So if you compare these two expressions, then we can see that we are actually we can actually see that these two integrals are the same because they are indeed the same. So what this tells us is, in fact, this unknown density function of y, f sub y, can be obtained through the density function of x by replacing x by inverse function of the transformation. In this case, half of y, express this g of x inverted, expressed in terms of y. And this half part comes from what? You invert the function and take the derivative with respect to y, then you will get half, right? So that half corresponds to d dy of inverse of g, which is indeed, in this case, half of y. So that's it. So that should give you a little bit of intuition why the theorem, how the theorem is stated. So in case we have nonlinear function of g, nonlinear function of x for g, this theorem stays, but as long as this function is monotone or one-to-one within the support of x. Okay, so that is the end of this theorem.